All right, let's talk about something incredible. We're looking at a steam turbine. I mean, this is a colossal piece of precision engineering. It's the kind of machine that can power an entire city. But here's the crazy part. For all its immense power, it has a surprising weakness. It's actually incredibly fragile, especially when you're just, well, turning it on.
And that really brings us to the central question here. You've got this massive beast of metal, right? It's built to handle steam that's over 500 degrees Celsius, and it's spinning at thousands of RPM. So what could possibly happen if you just, turn it on too quickly? Just flick a switch and let her rip? Yeah, the answer is, well, it's pretty much what you'd fear most: catastrophic failure. We are talking about a multi-ton rotor literally tearing itself to pieces. And that's exactly why starting one of these things isn't like flipping a light switch. Oh no, it's a super meticulous, hours-long procedure where even one tiny mistake can lead to absolute disaster. So why all this extreme caution, right? What's the big deal? Well, it all comes down to one single hidden danger. Every single part of this long, drawn-out process is designed to fight this incredibly powerful and destructive force called thermal stress. You know how if you drop an ice cube into hot water, it just cracks immediately? That's thermal shock. Now just try to imagine that same idea, but on a massive, multi-ton metal rotor. When that superheated steam hits the cold metal, the outside surface heats up and expands in a split second. But the inside, the core, it's still cold and contracted. It's like this insane tug of war that pulls the metal in opposite directions, creating these huge internal forces that can literally rip it apart from the inside out. And this quote right here, it comes straight from the operator's manual, and it really just drives the whole point home. The entire purpose of this whole startup procedure is to protect the turbine from cracking due to fatigue caused by these temperature changes. That's it. Every single step we're about to go through serves that one critical goal. Okay, so how do you actually fight this thermal stress? Well, the solution is a slow, methodical, and super carefully measured startup. But here's the thing. It's not a one-size-fits-all deal. The whole procedure changes completely depending on one key thing. Is the turbine cold, warm, or already hot? And this table just lays it out perfectly. If that turbine is totally cold, we're talking below 150 degrees Celsius, it's going to take almost 3 hours, a full 175 minutes, to gently bring it up to full power. But look, if it's already hot because it was just running, you can cut that time by more than half. It's simple, really. The warmer it is, the smaller the temperature shock, and the faster you can safely push it. But before you can even think about starting that slow warm-up, you've got to get your ingredients just right. Seriously, it's like cooking. If your raw materials are off, the whole thing is going to be a disaster. And for a steam turbine, the two main ingredients are the steam itself and the lubricating oil. I mean, just look at these requirements for the steam. This is not just clean water, okay? This is a level of purity that is almost hard to believe. We're measuring things like sodium and chlorine in parts per billion. A part per billion. At these insane temperatures and pressures, even the tiniest foreign particle acts like a sandblaster, just slowly eating away at the turbine blades. And it's not just about being clean, it's also about the state of the steam. It has to be superheated. That means its temperature has to be raised at least 55 degrees Celsius higher than its boiling point. Why? It's absolutely critical, because this gets rid of every last drop of moisture. And trust me, at the speeds these things spin, a single water droplet hits a turbine blade like a tiny bullet, causing damage over time. It has to be perfectly, totally dry. And of course, that steam temperature has to be matched perfectly to how hot the turbine already is. So for a cold start, you're using relatively cooler steam, maybe around 300 degrees. But if it's already warm or hot, the rule is that the steam has to be just 50 to 100 degrees hotter than the metal itself. See? It's all about gently introducing that heat, just to keep that thermal stress as low as possible. Okay, so ingredients are ready. Now it's time for what honestly feels like a mission control countdown for a rocket launch. It's this massive checklist of systems, and every single one has to be perfect before you can even dream of letting that first wisp of steam in. And this list goes on and on. First, you check all your instruments. You can't fly blind, right? Then you get the lube oil system going to protect all the bearings. And this next one is critical. You engage the turning gear.
A huge rotor like this can actually sag under its own weight if it just sits there. So you have to slowly rotate it for at least 4 hours to make sure it's perfectly straight. And then you start the pumps to create a huge vacuum in the condenser, because that vacuum is what literally sucks the steam through the turbine. It's essential.
And this is where the level of precision just gets mind-boggling. After hours of turning just to make sure it's straight, the wobble in that massive rotor shaft, what the engineers call eccentricity, it cannot be more than 0.0762 millimeters. Do you know how small that is? That is less than the thickness of a human hair. If it wobbles any more than that, the whole startup is called off. It's a no-go.
And the complexity just goes deeper and deeper. This diagram, this is straight out of the manual. It shows just one small part of the prep, the gland seal system. I mean, think about it. How do you keep a powerful vacuum inside a giant metal box when you've got a massive spinning shaft sticking out of both ends? Well, this is how. It's this super clever system that injects steam to create pressure barriers, sealing the gaps. It's a whole complex machine just on its own, with its own startup that has to be done perfectly before the main event can even start.
All right, so after hours and hours of prep, every system checked, double-checked, triple-checked, it's finally time. This is the moment of truth. They call it the impulse start. It's when that main steam valve is finally cracked open and the beast begins to wake up. And this startup curve, this shows you exactly how it all plays out. Just look at how gentle this is. That line on the bottom is time, all 175 minutes for a cold start. And those lines slowly creeping up, that's the turbine speed, the steam pressure, the power output. It is so clearly a marathon, not a sprint. The whole time, operators are glued to their screens, watching the instruments like hawks, monitoring the rotor's expansion, the vibrations, and especially those critical temperature differences. Just making sure everything stays in the safe zone as the whole machine warms up nice and even. Which, brings us right back to where we began. This quote just sums up the entire philosophy perfectly. All of this complexity, every single item on that checklist, every temperature reading, it's all about one thing: choosing a reasonable temperature change time. And that's how you keep that hidden killer, thermal stress, under control. It is just an incredible display of engineering and, honestly, pure discipline. And it really leaves you with a final question, doesn't it? If it takes this much painstaking precision just to turn the machine on, what in the world does it take to keep it running safely 24/7 for decades on end?